Hello everyone, I've been asked by a couple of you to do a review about reaction rates, so I'm just going to go through this quickly, and this is, in case you can't remember, Unit 3 of the specification. So a lot of this topic is a review of stuff you already learnt at GCSE with a couple of extra bits added in. So first of all, how do we measure the rate of a chemical reaction? There are two ways that you will do that. You either measure how fast a reactant is used up, or you measure how fast a product's formed. So most of you at GCSE will have done this one. You'll have maybe added some magnesium to hydrochloric acid, and you'll have measured how quickly the hydrogen gas is formed. But you could also look at how fast a reactant is used up. Either way, what you're essentially looking at is the change in something, change in concentration, change in mass, and dividing it by the time. So time always goes on your x-axis, and the other variable on the y-axis. What you'll find with the chemical reaction is that at the start of the reaction, when the concentration of the reactants is high, the rate of the reaction will be at its fastest. And then as those reactant particles get used up and turned into product, their concentration decreases obviously, so the rate of the chemical reaction decreases until it eventually levels off and there are no more reactant particles left, and the rate becomes zero. So what factors affect the rate of the chemical reaction? This is what you would have done at GCSE. So you'll have talked at GCSE about changing the concentration, changing the pressure, only if we're talking about gases, changing the temperature, adding a catalyst, or changing the surface area. Now for the purposes of A-level, the three that they focus on in terms of the specification are the concentration and the pressure, and adding a catalyst. So what makes a chemical reaction happen? Again, you should have done at GCSE this concept of collision theory, which says that in order for a reaction to take place, reactant particles have to collide with one another. It's not quite that simple though. The example that I frequently use is a piece of paper. So if you think about this bit of paper in front of me now on my kitchen table, it is being bombarded with oxygen molecules from the air around us, but the piece of paper isn't burning in front of me. Yet, in theory it should. Paper, oxygen, why is it not burning? And it's because the activation energy of the reaction is quite high, so it needs more energy. So although the paper and the oxygen molecules are colliding with one another, those collisions haven't got the activation energy or higher, so they're not energetic enough. And we need to give the particles more energy, i.e. increase the temperature, and then it will start to burn. We've talked about that at GCSE, we've done activation energy previously. The bit we don't talk about is this point here, which is this concept that not only must the particles collide with sufficient energy, but they must collide with the correct orientation. So physically they've got to hit one another in the right place in order for the collision to be successful. It might help you to think about this in terms of, if you think about an ionic equation, when you write out a full ionic equation, one of the steps to do that is that you delete the spectator ions. So the ions that appear on both sides of the equation, we cancel. So if you imagine if it was the spectator ion section of the molecule that was colliding with another one, nothing's going to happen because they're not involved in the chemical reaction. So it's the physical way that the particles come into contact with one another is important. Right, so concentration and pressure. This is a review from GCSE. So if you increase the concentration in a chemical reaction, what you're doing is putting more particles in the same volume. That means the particles are more crowded, and that means the collision frequency increases. They're going to collide with one another more frequently because they're more crowded. And that means that there are more successful collisions per second. I've put in a given time period here because you could talk about more successful collisions per second, per minute, per hour. The standard is seconds. Pressure's really similar, but we're talking about gases. Excuse my dog drinking in the background. So pressure's very similar, but we're talking about gas molecules. So there's two ways that you can increase the pressure in a chemical reaction. You can either reduce the volume, so you have the same number of particles but in a smaller volume, or you keep the volume the same and you add more particles to it. Either way, it doesn't matter. The particles are just going to be closer together. So just like concentration, the particles will be more crowded, and that means they'll collide with one another more frequently. And again, that means there'll be more successful collisions per second. Now, when you're writing your answers to this in the exam, what's really important, what gets missed, is this frequency concept. So people will put that there are more successful collisions because the particles are more crowded, but they forget about the frequency. So we'll say there are more successful collisions per second. Okay. And finally, looking at how we calculate the rate of a chemical reaction. Again, you did this at GCSE. You would plot a graph of your results. As I said a minute ago, time will always be on the x-axis and your other variable on the y-axis. And to calculate the rate of the chemical reaction, all you need to do is calculate the gradient of the line. So you'll do difference in y divided by difference in x. There are some good examples of that. I'm just checking the page number, page 147 of your textbook. At GCSE, they tended to give you areas of the graph where it was already a straight line. At A-level, you're more likely to get something where you need to draw a tangent to the line. So I would suggest you, if you need to remind yourself, have a look at page 147, and it will show you about drawing tangents to the line and calculating the rate from there. And remember that your units are just taken from the graph. So if you've got grams on the y-axis and seconds on the x-axis, your units will be grams per second. Or if it was concentration per second, concentration and seconds on the y-axis, it would be moles per decimeter cubed per second. So you can work out what your units are by looking at your graph. And then the final bit of this section, before it goes on to the Boltzmann distribution, which we've already talked to you about, is about the use of catalysts. So, important things about catalysts. The first thing is that they're not used up in a chemical reaction, and they always get regenerated at the end. And catalysts can work in two ways. They can either provide a surface for the reaction to take place on, or they'll react with a reactant to form an intermediate, and then that intermediate will break down, form the product, and the catalyst will be regenerated in that section. So we've already talked previously in a video about how catalysts work. Here's a quick energy profile diagram to show you. So remembering that they don't just lower the activation energy, that's not physically possible, but what they do is provide an alternative pathway that has a lower activation energy. And you can see that just demonstrated here on an exothermic and an endothermic reaction. So you've got your normal reaction here, uncatalyzed, and the catalyzed one here with a much smaller activation energy each time. And the only other thing you need to know about catalysts is the two different types. So bear with me, there you go. So you have homogeneous catalysts are where they're in the same physical state as the reactants. And if you look in your textbook on 149, page 149, there's a couple of examples of reactions there for you. Heterogeneous are just a little bit more complicated. The reason they're more complicated is because the catalyst is in a different physical state to the reactants. So what happens in a heterogeneous catalyst is that the reactant molecules are adsorbed, that is just a posh word for weakly bonded, onto the surface of the catalyst. And then after the reaction's finished, the product molecules will leave the surface of the catalyst, and that's called desorption. Most of the examples of catalysis that you will think of are this second one. So catalytic converters in cars, the Haber process, the contact process, they all involve heterogeneous catalysts where they're in a different physical state. Okay, thanks.